Now, we can relate the Green's function to the fundamental solution of Laplace's equation. And we didn't work this out, but in the case of the one-dimensional Laplace's equation, we can write the fundamental solution like -1/2 the absolute value of x minus y. So in this case, g of xy is going to be equal to this fundamental solution plus a term that's meant to make corrections on the boundaries, okay? Because obviously this is not going to vanish right where we need it to, okay? So we need to build in those corrections to the boundaries, and that's one of the big ideas of building Green's functions is that you have to take a fundamental solution and correct for the boundaries, okay? So we want this boundary correction term to be it needs to satisfy the homogeneous version of our equation. For all y that live in 0 to 1, okay? And also, since g of 0 y is equal to g of 1 y equals 0, okay? Then we know that phi y of x is equal to minus our fundamental solution, okay, at x equals 0 and x equals 1, okay? So that's our setup here. So we need it to satisfy the homogeneous solution for x goes from 0 to 1, okay? And phi y of 0 is equal to minus big phi 0 y. Little phi y 1 is equal to minus big phi 1 y, okay? Phi y of x is equal to a of yx plus b of y, right? Should just be a linear function because it vanishes when you differentiate it twice. And these are constant in x, so they'll go away as we differentiate. Now note that if we apply our first boundary condition, we get that b of y needs to equal whatever big phi 0 y is minus big phi 0 of y, right? So that's going to be minus a half y, so we just get y over 2. Okay. And then our other boundary condition is that a little phi y of 1 is equal to a of y now plus y over 2. And this is equal to 1 over y minus 2, because that's what big phi minus big phi 1y is. And we get a of y is equal to a half minus y. Okay. So our full boundary correction term then is x plus y over 2 minus xy. Okay. Now, did this work? Okay. Let's go ahead and check. Okay. Well, we have now that gxy is equal to minus a half x minus y plus x plus y over 2 minus xy. So when x is less than y, we have that g of xy is equal to, it would be minus this, right? So we get back a x minus y over 2 plus x plus y over 2 minus xy. Of course, we can cancel these terms out now, and we get x times 1 minus y, which if we look back here, indeed we get x times 1 minus y when x is less than y. Okay? Okay. Now our other term then is going to be when y is less than x. So we get g of xy in that case is equal to y minus x over 2 plus x plus y over 2 minus xy. We cancel out the x's in this case, and we get y times 1 minus x. Okay. All right. So indeed, we have that u of x is equal to the integral from 0 to y, g of xy, f of y, dy. Great. Okay. So what about the case where we have inhomogeneous boundary conditions? Okay. What about the case where, let's say, u of 0 equals a, and let's say u of 1 equals b, and then we still have our one-dimensional Poisson equation? Okay. Well, we start by finding the solution. Okay. Call it ui to ui prime prime equals 0. U of 0 equals a, u of 1 equals b. Okay. And this will be our boundary condition solution. Okay. So it's interesting to note that dg dy, right? We've already worked out what this is. Okay. This is going to be equal to minus x whenever x is less than y, and 1 minus x whenever y is less than x. Okay. And we know that d2 dx squared of dg dy here, okay, is equal to 0, basically almost everywhere. Okay. Also, we can look at the boundary terms. So dg dy 0, 1 is equal to minus dg dy 1, 0, right? Because if I plug in 0, 1 here, then x is less than y, and I get a 0 here. And if I plug in 1, 0 here, then x is greater than y, okay? And I have 1 minus 1, so I get back 0, right? So this is 0, okay? Whereas dg dy of 1 from below and 1 is equal to minus dg dy 0 from above, and 0, these are both equal to minus 1. Okay. So what this implies then is that u of x can be written like minus b dg dy x1, okay, plus a dg dy x0 plus the integral from 0 to 1 g of xy f of y dy, and that will then be equal to a plus x times b minus a, okay, plus the integral from 0 to 1 of g of xy f of y dy. Okay. So Good. So then u of 0 is equal to A and u of 1 is equal to B, basically as expected, right? Because if we plug in 0 here, right, everything vanishes except the A. If we plug in 1 here, then I get a B out in front, and this term vanishes, right? My integral vanishes, okay? So this is equal to this incorporates essentially our boundary conditions, okay? So we can get boundary conditions satisfied, okay, by taking terms basically involving our Green's function, okay? And that's no accident, right? It's a little mysterious here what's going on, but this is setting us up for what's going to happen in the case of two-dimensional Laplace and Poisson problems, okay? One more approach before we move on, okay? Would be, let's say, if we have u prime prime of y equals 0, y goes from 0 to 1, and b, we have g sub y of x y equals delta of x minus y, and y goes from 0 to 1, okay? Now, if we multiply a by g, and we multiply b by u, and then we subtract and integrate, okay? What we end up with is the integral from 0 to 1 of minus g u prime prime plus u g y y dy. And this is equal to minus the integral from 0 to 1 of delta of x minus y u of y, okay, dy. And this is equal to what? Just minus u of x, right? So what's cool about this then is that this is another way of getting a solution, okay, of a much more general form, which is that you can integrate u times g sub y minus u prime g differentiated. But then by fundamental theorem of calculus, we can write this out as u1 g sub y x1, okay, minus u prime g of x1. But remember, this is just going to be 0, okay, minus u of 0 g sub y x0, okay, plus u prime g x0, right? Which this thing is going to be 0 right there, okay? So we end up with our solution in this case, okay, is going to be u of x, right, is equal to a times 1 minus x plus bx, right? Which is our additional term, right, that we're adding on that accounts for our boundary conditions in this case, okay? So this gives our solution satisfying boundary conditions, okay? All right, so we have a solution. It involves a Green's function, okay? We show that it exists, right? But what about the other aspects of well-posedness, right? We already have existence, right? So let's try a crack at uniqueness, okay? So U1 and U2, they solve let's say our Laplace equation with inhomogeneous Dirichlet boundaries. You know where we're going with this, I hope. Let's say we define W. Well, then, of course, we have, sorry, this was the inhomogeneous Poisson's equation. Well, then W just satisfies the Laplace equation with 0 Dirichlet boundaries, homogeneous Dirichlet boundaries, okay? I can actually just immediately write down a solution to this using the Green's function, right? And straight away, we see that W is 0, okay? What about continuous dependence, okay? Well, let's work a bit more on this, right? If I take the infinity norm, okay, of F in this case, this would be the supremum over X of the absolute value of F, okay? And let's also take the L1 norm. That's just going to be the integral of the absolute value, okay? And now suppose that U1 and U2, they solve the original boundary value problem, okay? But either the right-hand side is F1 or F2, right? Well, then what we can say is that U1 minus U2's absolute value is equal to G of X y, F1 y minus F2 of y, dy, absolute value of that, okay? We can bound this from above by G of xy, absolute value, F1 minus F2, dy, okay? And then, of course, we know that the Green's function, okay, is going to be finite, even it's already positive. So, and we can bound this from above by the infinity norm or the L1 norm here. Okay. So we have these three features, right, that we need. We have continuous dependence, and we have uniqueness in this case. Okay. And all of them come from this formulation of the solution to the Poisson equation in terms of Green's function, right? Okay.